talking about Twistor analysis of a parabola.
Okay, thank you. So I had breakfast this morning in Churchill College, and I was reminded of the importance of circular cones because there's a sculpture of a circular cone tangent to a tetrahedron on the lawn. I was also reminded of the importance of general relativity because they display a book by their third master, Hermann Bondi, who was for many years at King's College London and did work on gravitational waves, which nowadays I'm sure would be a great impact case study and so on. There'll be a few cones at the end here. I'm trying to sort of explain some elementary thing in terms of complex geometry. There'll be some obscure links with general relativity through the Weyl curvature tensor. So there will be different things coming together, I hope, in this talk. I'm embarrassed not to be talking about G2. I enjoyed the talks this morning, but I was here briefly last week and people were talking about twistors, so that's why I chose this topic. But there will be an overlap, I think, with Dimitri's talk from yesterday. So the idea here, just to explain what I'm trying to do, I mean, you all know that if you have a parabola, rays coming in parallel to the axis from infinity, like here, get reflected and go through the focus, the sort of principle of the parabolic microphone. But you should really think in terms of cones. You see, if you put the parabola in 3 dimensions, put it on the table and think of 3-dimensional space, then you can extend these sort of lines and consider the circular cone whose axis is the tangent line to the parabola. And it turns out that wherever the point is on the parabola, this cone will always pass through another fixed parabola, the blue parabola, which is in a plane orthogonal to the original one. Or there's a sort of duality here. You can look at the blue parabola and you can say, what is the locus of all the vertices of the double cones, the circular cones that go through that blue parabola? And the answer is the red parabola. So there's this sort of elementary geometry of, you can also do this for a hyperbola and ellipse. If you start with a hyperbola, then you get an ellipse and vice versa. And this actually came up through some Twistor geometry, so I want to tell you a bit about that. So I'm going to try and divide the talk into 3 parts. The first part is just some general theory about orthogonal complex structures on Riemannian manifolds and Riemannian Twistor spaces in general dimensions. Then the central part of the talk will be looking in detail at what you can do with the well-known Penrose or Hopf vibration from CP3 to S4, but I'm thinking of S4 as the Quaternionic projective line. So this was the map that was sort of important in Dimitri's talk. And then I'll explain how this links, rather surprisingly, with a theory of quaternionic regular functions. Not the Foyter regularity, but another type of regularity, analyticity, that's been studied for the last 20 years or so. And it turns out that you can interpret quaternionic power series using this Twistor approach. So, you see, my point of view is I'm starting from a Riemannian manifold. I'm not starting from a complex manifold like in, say, Calabi-Yau theory, in which you have a complex manifold, you're looking for a compatible metric. I'm starting from a Riemannian manifold, even dimensional. And I'm trying to look for complex structures that are compatible with that metric. So an orthogonal complex structure is exactly what it says it is. It's simply a complex structure that's for which the usual J is an orthogonal transformation. So it's the usual compatibility. And as you all know, it produces a 2 form. You can just put in J in one slot and you get a 2 form. If the 2 form were symplectic, were closed, this is non-degenerate, it would be a Kähler manifold, but I'm not, of course, assuming that. Since I'm focusing on the metric, it's natural to consider the associated Levi-Civita connection and its curvature. And for me, really, the fundamental lemma here is that if you have a complex structure, that means the Nienhaus tensor is 0, and you take two vector fields of type 1, 0, then the covariant derivative of nabla xy is also of type 1, 0. Now, you see, if you skew that fact, nabla xy minus nabla yx, that's like the Lie bracket. So that's well known to be of type 1, 0. That's the Nienhaus tensor. This appears to be a stronger statement, but actually it's equivalent. And that's the subtlety. The subtlety is that these two statements are equivalent. And as an immediate corollary, if you define the curvature endomorphism in terms of the covariant derivative and Lie brackets and so on, you see immediately that, again, with a complex structure, an orthogonal complex structure, you can deduce that if you have three vector fields of type 1, 0, and you take r, x, y, z, this is also of type 1, 0. And I think this is probably very familiar to GR people, because I think in a slightly different interpretation it's to do with shear free congruences or something. I think it's a well-known phenomenon, but in which orthogonal complex structures become some other object. So the point is it has an effect on the curvature tensor. The existence of one of these orthogonal complex structures gives actually quite a big constraint on the curvature tensor. In terms of representation theory, it's very easy to say what it is. We're simply saying, by the time you take the inner product of this with a fourth vector, we're simply saying that the curvature tensor, the Riemann curvature tensor, has no component of this sort of pure type. You know, thinking of the curvature tensor sort of skew in two indices, skew in the other two. If you plug in everything of the same type, you get 0, either 2, 0, 2, 0 or 0, 2, 0, 2. And you can analyze that condition. It's well known in 4 dimensions, been a lot of analysis, but it's quite interesting in higher dimensions. So you see, in higher dimensions, we can do a sort of asymptotic count of the conditions that this constraint imposes. So here's a quick summary. The space of curvature tensors is the kernel of, by the time you put in the first Bianchi identity and so on, it's the kernel of this linear mapping at each point. And its dimension is, for large n, if you forget the lower order terms, it's 4/3 n to the 4th. Whereas the condition which I gave you on the previous slide is a similar sort of condition, but it involves sort of forms of pure type. And that condition only affects the Weil tensor, because you can't, if you're saying this component is 0, you can't do any contraction from that component. You can't get a Ricci component. So it only affects the Weil tensor. So this condition of having an orthogonal complex structure is really telling you that the curvature tensor has 0 component in some subspace of the space of Weil tensors. And the dimension of this subspace is asymptotically a 6 n to the 4th. And you see, that's rather surprising, because this condition, it doesn't depend, I mean, the ratio of these two doesn't depend to first order on n. This is just an eighth of this. Okay? So we all know now slogans are important. So the slogan here is that if you have an orthogonal complex structure, for large n, it wipes out an eighth of the Weil tensor. Right, slogans aren't always accurate. This is accurate if you have one, but if you have several, of course, they might not be independent. So you can't sort of, it's not true if you've got 8 almost orthogonal complex structures and the Weil tensor is 0. If you've got enough, the Weil tensor will be 0. Now in 4 dimensions, just to say how strong, I mean, we can be more specific. In 4 dimensions, this subspace, orientation plays a role. So the Weil tensor splits into 2 halves. You can just look at half of it, and this subspace actually really concerns, say, the positive Weil tensor. And the positive Weil tensor has dimension 5, so it knocks out 2 of the dimensions. And you can be very explicit, actually, if you use spinors, you would say that the Weil is half the Weil tensor is a quartic polynomial in spinors, and we just get 4 roots which come in conjugate pairs. But to be more sort of real differential geometry, we can just, the Weil tensor is a self-adjoint 3 by 3 matrix. It's going to have eigenvalues, trace 0, eigenvectors, orthonormal bases of eigenvectors, and it turns out that the condition, if you have an orthogonal complex structure, it actually has to be one of these, the corresponding two form, I can tell you what it is by telling you what its two form is, the corresponding two form has to be one of these four objects, corresponding to the four roots, if you like, of the Weyl tensor. And that's a remarkable fact, because it means if you have a metric, and you want to know whether there's an orthogonal complex structure, you just have to look at the Weyl tensor. You have four roots, generically, and you have to work out whether, up to sign, there are just two roots. You just have to work out whether or not these are actually they're going to correspond to almost complex structures. You've just got to decide whether they're complex or not. And this leads to the theory of, for example, bi-Hermitian metrics. You can ask, do there exist, it was an unknown question for some years actually, do there exist metrics for which the plus Weyl tensor is non-zero, but for which both of these pairs of roots correspond to integrable complex structures? The answer is yes. We now know there are lots of examples through work of Apostolov, Gordashov, and so on. Now let me now interpret what's going on here using Twistor spaces. So the idea is that since we're fixing the metric and say an orientation on the manifold, we're interested in, if we want at each point a complex structure, we want to reduce the structure group from SO2n to UN. So at each point we're sort of interested in this space here, which is a Kähler manifold, a Hermitian symmetric space. And you can actually, these spaces, you can sort of build them inductively using this fibration. If you start with the even dimensional sphere as a natural bundle with this as its fibre, and the total space will be the next one in the series. And that allows you, actually what's going on here is you can just take an even dimensional Riemannian manifold, you can just take the associated bundle whose fibre is Zn, and this is the so-called Twistor space or Twistor bundle of the Riemannian manifold. If you do that for the sphere, you get, remarkably, the Twistor bundle is just the next thing in the series, which will be the fibre of the next sphere. So this Twistor bundle, if you start with an even dimensional Riemannian manifold, it's a sort of tautological construction. It just means that if you have a section of this bundle, that simply corresponds to an almost complex structure on the base that's compatible with the metric. Because everything here depends on the metric. The metric is given, otherwise you couldn't construct this. So if you have a section, you have a compatible almost complex structure. The question is it integrable? And it's well known, I'm just really giving a summary here, it's well known this bundle, has a natural almost complex structure called J1. In fact, there are two, but J1 is the natural one. And there's a sort of tautological fact that if you have a section, that corresponds to an integrable complex structure if the section is a J1 holomorphic section. If the map from M with that almost complex structure to Z with the J1 almost complex structure is a holomorphic or pseudo-holomorphic map, if its differential commutes with the J's. Now, if you do this in 4 dimensions, what's going on is that the fibre in 4 dimensions, as Dimitri mentioned, is just the 2-sphere. Z2 is just the 2-sphere. And you'll always, the Nienhuis tensor in general will not be 0. It will only be 0 if the manifold has W plus 0. But there will also be there will always be at least 2 sections or 4 sections with signs where the Nienhuis tensor is 0, and those are the roots which I talked about earlier. These roots here define sections of the Twistor space for which the Nienhuis tensor is 0. That doesn't mean that those sections correspond to complex structures, but if they are complex structures, then they'd have to be one of those 4. That's a sort of interesting interpretation of what I said. Now, I I just wanted to give this introduction to sort of tell you what's underlying the more specific theory I'm going to talk about later on. But I thought it might be, to finish this first part of the talk, I thought it might be good to mention just S6 and what goes on with 6 manifolds. So, as I mentioned, and we'll see in a different way in a moment, the set of almost complex structures compatible with a metric on R4 and an orientation is just the 2-sphere, or CP1. If you do this on a 6 manifold, at each point you're looking at the almost complex structures compatible with a metric and orientation on R6, that's CP3. But in general, these Kähler manifolds Zn, they're sub-varieties of some projective space. They're the so-called varieties of pure spinors. And there are various ways of defining these varieties of pure spinors, all understood by Lecartan. Here's perhaps the most elegant way that you take, we're talking about spin 2n in general. If you lift SO2n to spin 2n, then spin 2n has half its spin representation I call delta plus. Look at spinors here. Now when you take the tensor product of such spinors with themselves, you get delta plus tensor delta plus is a sum of exterior powers for SO2n, and the top component would be lambda n plus, which is the sort of half of the middle exterior power. So if when you take this tensor product, you're only in this component, in general you'll have lots of other components when you take the tensor product. If you're only in this component, then that defines this, projectively, this manifold. Now it turns out this condition is vacuous for n is 2 and n is 3, that's why you get the full projective space, but it gives one condition, you just count dimensions, it gives one condition if n is 4, and that means that Z4 is going to be a quadric, a complex quadric in CP7. It is in any case a Kähler manifold, and you see if you do this for S6, if you just do the fibration I mentioned, you'll have S6, the fibre now is Z3, which is CP3, and the total space we now know is Z4, which is this quadric in CP7. Now, of course, there are globally almost complex structures on S6. There's a G2 invariant one, so certainly there are sections of this bundle. If you had an orthogonal, if you have an integrable section, a section that corresponds to an orthogonal complex structure, then this would be a complex submanifold from what I said before, because of this sort of self-holomorphic property. If you had an integrable complex structure, this would be a holomorphic submanifold of this, and the corresponding complex structure is indeed the standard complex structure on this Kähler manifold, and so this would be a submanifold of a Kähler manifold, and therefore its second Betti number would be non-zero, but it's diffeomorphic to S6, which is impossible. So that's a very simple argument which Claude Lebrun wrote up, which shows you that S6 can't have, S6 with its round metric, or equivalently with its conformally flat structure, Weil tensor 0, can't have any orthogonal complex structure.
For small perturbation of this metric, like, I mean.
Well, I mean, you see, this is very special, this situation, because in this case, the complex structure on this Twistor space is integrable because this is conformally flat.
For example, like this, if you perturb a little bit the metric on S6, yeah, then I guess almost complex structure upstairs also will be only slightly perturbed.
Yes, but it will be typically non-integrable then.
But then, I mean, then again, same reason will prove the result, because it will be tamed by symplectic form still, and S6 is non-symplectic. It sounds like this is...
Well, I think the Kähler condition is important. You're saying you can get it from the symplectic condition, maybe. I mean, this is the last slide in the first bit. I wanted just to propose this. I mean, what one could do is actually, one could look at a more general metric on a 6 manifold. And from what I told you, if you could work out the Weil tensor, you'd have considerable constraints on the existence of complex structures. Now, it turns out the Weil tensor, if you analyze this, you can actually, I won't go through the details here, but because of this special isomorphism, you can think of the Weil tensor as an element of this tensor product, a lambda 3 plus, these are complex vector spaces, lambda 3 plus tensor lambda 3 minus. You know, you probably know on a 4 manifold, lambda 2 plus tensor lambda 2 minus is the space of trace-free Ricci tensors, but in 6 dimensions, it contains the space of Weil tensors. So, you know, one could in theory look at orbits of this and try and analyze, try and at least extend this, generalize this result, perhaps in a different way. Since I'm not talking about small deformations here, I'm taking deformations and classifying them by the nature of Weil tensor. And try and rule out many cases, you know, in which you're looking at more general metrics. That was my idea.
Is there any hope of ruling out every single orbit type?
Well, I mean, I'm not that optimistic. I mean, I'm not going to propose that, but certainly it's worth. I think this is worth looking at. Okay, let me move on. So the sort of main part of this talk is I wanted to tell you in some detail how to use this Penrose Twistor theory to understand orthogonal complex structures. So for me, really, this slide contains the key calculations you need. So if we think of S4 as the quaternionic projective line, then this map here, this Hopf vibration, is just the map which takes a complex line to the quaternionic line that it generates. So you see there's this J acting on CP3 because CP3 comes from C4, which is H2. So you've got multiplication by J, say on the right, and that will give antilinear involution of C, well, J squared is minus 1 of C4, and therefore this will give you an antilinear map on CP3, and then therefore you can map a point to its quaternionic, the complex line maps to its quaternionic line. I've taken rather strange coordinates here, but I've sort of taken homogeneous coordinates. This will be convenient, and I think, you know, Penrose people would probably use primed spinors and unprimed spinors is probably the same thing. But explicitly, this map simply does this. We take 4 complex numbers, which are the homogeneous coordinates in CP3, and we just map them to these 2 quaternions. We just combine these to get 2 quaternions. And then you can, by using right multiplication by quaternions, because we're in the projective space, we can make the first coordinate 1, provided I put a 1 here, so that's not 0. And so we end up with a single quaternion. And you see, since I'm using right multiplication, I can get rid of the first one by multiplying on the right by its inverse, but then I put it on the other side. So what I get is that this combination here is just a quaternion times this quaternion. Now let's suppose that the quaternion Q, which is a sort of affine coordinate on S4, is Z1 plus JZ2, then I get these relations. Okay, so they're so important, I'm going to copy them down. I'm using Z1 and Z2 are the coordinates on R4. I'm thinking of R4 as C2, but these are to be thought of as Euclidean coordinates. They're not holomorphic in any sense. It's just I'm using complex numbers for convenience to parametrize R4. And whereas the W's are sort of holomorphic objects, these are the coordinates on complex projective 3 space. So W1 is just Z1 minus U Z2 bar, and W2 is Z1 Z2 plus U Z1 bar. Okay, these are holomorphic coordinates because these are the coordinates on CP3, and these are the sort of Euclidean coordinates. And then you can go a long way actually from these equations. So in particular, what we can do is we can now think of taking u to be constant. Okay, suppose we take u to be constant. So remember, u is just a coordinate on complex projective 3 space. So if we just take u to be constant, I'm actually defining I'm putting an equation between these two coordinates. I'm defining a complex projective plane. I'm just defining a linear subspace of CP3. So taking u constant just singles out a projective plane. That plane will contain the fibre at infinity. This is the point at infinity that you add to R4 to get S4. So, you know, CP2 topologically is the blow up of S4 as a point. So I'm just taking it to be 1 over R4, and but the point at infinity is sort of the point at infinity in S4 becomes a line in CP2. And the point is then that the W1 and W2 are sort of holomorphic functions. U is now constant. And so W1 and W2 define a new complex structure on R4. It's going to be a constant structure because U is constant. But instead of taking the standard complex structure, which would be sort of Z1 and Z2, we've sort of deformed it by adding U. And I therefore have a new complex structure for which the W's are holomorphic. Or if you prefer, if you just differentiate the W's, you should get 1-0 forms. So the 1-0 forms of this new constant complex structure look like that. And all I'm doing here is I'm just parametrizing the almost complex structures that are compatible with the metric. But I'm using a complex parameter u, which belongs to the complex projective line. Normally, people would say that you get a two-sphere of almost complex structures, which you can think of as the two-sphere in lambda 2 plus. Well, you can relate these directly. In fact, it turns out if you do the calculations that the coefficients here are just the sort of usual formula for stereographic projection. So you have this two-sphere, or u is a complex number, but you can extend it to infinity. You see, if u is infinity, that means you've just, if u is infinity, you're just taking the complex conjugate of the usual complex structure. You're just taking minus j, where j is the usual complex structure. So I'm just really explaining, you're just using this to parameterize the constant complex structures which you can define on R4. And then, of course, there's this question you can ask, well, suppose you have an orthogonal complex structure. You take the Euclidean metric on R4, you take a complex structure that makes this Hermitian, so complex structure which is orthogonal with respect to this metric, what could it be? Okay, it was generally accepted that it has to be it has to be constant, therefore one of these. I think maybe John Wood wrote down a proof with Paul Baird in their book on harmonic morphisms, but this is sort of generally accepted, this result. Working with Jeff Yoklowski, we actually strengthened the result, so I want to tell you, before going on to an example in the second half of the talk, I want to just give you the strengthened version of this result. And to understand this, one needs to remember that on the fourth sphere we've got this group of conformal transformations. Now don't forget the condition, the starting condition I gave you for an orthogonal complex structure was simply the condition that the rotation, if you like, by j is an orthogonal transformation. But of course, if you change the metric conformally, that condition doesn't change. So this is really a conformal condition. We don't need the metric, we need the conformal structure. So everything's conformal invariant in this theory. So we should really look at what happens when we act by the conformal group. So the conformal group on S4 is the connected component here, and that's double covered by this sort of projective, well, it's the projective quaternionic, what shall I call it? Projective linear quaternionic, a group of Mobius transformations using quaternion on the quaternionic projective line. So this is the relevant group we're interested in. This is the group that preserves the Penrose fibration. Okay, we have the Penrose fibration CP3 fibers to S4. We want to preserve this in all our discussion, so it's no good acting on CP3 by the big projective complex group. We have to restrict the transformations to those that come from S4, and that's what this subgroup is. But the problem is this subgroup is no good fixing a point at infinity. Before I was effectively fixing a point at infinity. If we apply a conformal transformation, that could move from the point at infinity to a point in R4. So what we have to do really is to consider now having an orthogonal complex structure defined not necessarily on all of R4, because we know that just by moving one of these constant ones around conformally, we get something that's defined on R4 minus a point. So let's suppose we have something defined on R4 minus several points, or minus a small set. So if we have an orthogonal complex structure defined on R4 minus some closed subset A, provided the one-dimensional Hausdorff measure of A is 0, then it is the case that this J is effectively one of these over here with U constant. So it's conformally equivalent to one of these constant complex structures. And therefore it has to be defined not just on R4 minus A, but at least on R4 minus a point, or possibly on R4 if it's actually constant rather than just conformally constant. So that then sort of begs the question, what about other orthogonal complex structures? What about non-constant orthogonal complex structures? Where are these defined? There can't be any entire ones. This is a sort of Liouville theorem. Any entire one has to be conformally constant. But are there others that are not conformally constant on some big open subset of R4? Well, there are. I mean, for example, if A is a circle, as we'll see in a moment, you can get a completely new orthogonal complex structure, and this is what I want to talk about. But before I do that, let me just recap what we've done here. We've been looking, by my choice of coordinates, we've actually been looking at an open set of this Twistor bundle in which we've sort of removed a point at infinity, so we've just really been looking at R4, and that simplifies things because we can then basically what's left here, if we remove this line over infinity, we're left with a sort of product structure R4 cross CP1. So that's an open set of CP3. And so that's basically what I'm defining here. There is this open set of CP3 in which we just take our Euclidean coordinates, take an extra coordinate u, we map these to that, where the w's are defined over there. Now, if you forget about CP1, you just remove this possibility that u is infinity, then actually this becomes C. So this is just the product of C with R4, so this is basically R6. And this incidentally shows you that on R6, you see that this has a complex structure, obviously. And what's happening with this complex structure is that the induced complex structure on R4 depends on U. So this is not the complex structure on CP3 is not a product here. This is the so-called Twistor space of R4. As you go up and down, each copy of R4 comes equipped with a different complex structure. So this is what we call a warped product structure. It's a sort of the standard complex structure on CP3, restricted here to R6, becomes a sort of warped product structure in which it's changing. You're using one coordinate, the last coordinate, to sort of change the complex structure on the first two coordinates. Okay, and that shows you that R6, in contrast to R4, does admit non-constant orthogonal complex structures. So there's a whole theory of sort of how one might classify these. So it's sort of curious that that comes out of this construction. But I'm not going to talk about 6 dimensions anymore. Now the idea is this, that if we want to get something non-constant, we want to choose u non-constant. So we want to choose u to be a function of our Euclidean coordinates. That will give us a sort of graph here. Well, this is a multi-valued graph. The problem is that to get these things in practice, you want to take some sort of algebraic subvarat in CP3, so that will typically give you a multi-valued graph. But if this isn't multi-valued, then you're just defining u as a function. U is really this coordinate here. You're finding u as a function of z1 and z2 on R4. That would define you an almost complex structure again. So what is the integrability condition? The integrability condition is that this map, as I've said before, has to be sort of self-holomorphic. And if you write that down analytically, you get sort of this system of first order PDEs. And in particular, these are harmonic functions. So we're really looking to solve these equations. That's the point. If we can solve those equations, then we can define one of these non-constant orthogonal complex structures and investigate them. But rather than trying to solve these, as I said, I mean, we've got this sort of complete integrability here. I mean, we're working in CP3. All we have to do is write down a polynomial or something to define a subvarati, and we're done, except that f will be multivalued. So here's the simplest non-trivial example. So we dealt with the linear polynomials. They just give constant or conformally constant almost complex orthogonal complex structures. Now let's look at a quadratic example. So let's just take the quadric in the sense that this times this is equal to that times that. So W2, I'm using, remember, homogeneous coordinates, but the sort of simplest quadric to get the nicest sort of equation here, you just take the first coordinate times the fourth is the second times the third. And that is effectively saying that our function u, our graph u, is W2 over W1. Now if you just substitute in what W2 and W1 are, you then get this quadratic equation for u. And that's obvious that you're going to do that because we're talking about a quadric in CP3 now. So again, we've got S4 or R4. Over S4 we've got CP3. And we've got a quadric in CP3. So over each point here, P in S4, we've got a CP1. The quadric's going to generically hit that CP1 in 2 points. And those 2 points, we're just a matter of finding the coordinate u, and they're given, remember, z1 and z2 are the functions on R4. So for each z1 and z2 on R4, we can see what the 2 points on the fibre are where the quadric cuts it. And it's just a matter of solving a quadratic equation. But one's interested in this situation in the so-called discriminant locus, when these 2 points might coalesce, or when the whole fibre might be inside the quadric. And in this situation, I've chosen it very carefully, if the discriminant is 0, that these are just the real coordinate, these are just the real and imaginary parts of z1 and z2. If the discriminant is 0, if these just get a single root, in fact, the whole quadratic is 0 because x2 and y2, that gives z2 and y1. So actually what happens here is that you never get a single root. If these two coalesce, you have the whole fibre. Okay, so you can begin to understand how the quadric is mapping down to S4. This is a so-called real quadric because it's actually invariant by this J, which is the antipodal map on each fibre. So these two roots are always sort of J and minus J. But they can, there will be points where you get the whole fibre. So, I mean, the points where you get the whole fibre are given by these equations. That's just a line in R4. I mean, just we're saying x1 can be anything, but the other three coordinates are 0. That's a line in R4 which extends to a circle in S4. Okay, now I'm trying to explain it with these sort of old pictures here. So, you see, the quadric, a quadric is biholomorphic to CP1 cross CP1. It's topologically S2 cross S2. We're saying things go wrong downstairs on a circle in S4. So if we remove that circle, we get an open set, or remove the line from R4, we get an open set of R4. And that's like sort of removing this sort of circle here. So what's left is, I mean, over this circle you have all these twistor fibres. So you get the circle cross S2, you're removing that. So we're actually removing a circle cross S2. And what's left is S2 times a disk and S2 times another disk. Okay, and those are just the two branches of the quadric that are left. So basically we have this quadric in CP3. We know that generically it's 2 to 1. There'll be some points where you get the whole fibre. If you remove those points, you just get these two branches of the quadric, and each branch you can think of as S2 cross a disk. Each branch is just diffeomorphic to R4 minus a line. Once you've removed the bad stuff, which is a circle, we've removed, we have R4 minus a line, minus the real axis. And R4 minus a line, you can think of it in this way. It's, you know, if you're in 3 dimensions, you remove a line from R3, you automatically get the sort of magnetic field of the line. But in 4 dimensions, the natural thing you get is this orthogonal complex structure, because if you remove a line from R4, then orthogonal to this line you've got R3s. For fixed radius you have 2 spheres. So the whole thing is a 2-sphere cross a half plane. Any point in R4 minus a line corresponds to a point in S2. It corresponds to a point in this half plane and a point in S2. So what I'm telling you is that S2 cross a half plane is the same as R4 minus a line. And then it's obvious that there is on that open subset an orthogonal complex structure, because you can just put the standard, these are just real surfaces, you can just put the standard complex structure on these Riemann surfaces and take the product, and that will give you the key thing is it's orthogonal because of this picture, basically. It's another way of seeing it is that you can take the Kähler product here, but with Gaussian curvature plus 1, constant Gaussian curvature minus 1, when you take the product, you get something that's conform. You get something that's Kähler but conformally flat. So it's conformally equivalent to the flat metric. So what I'm trying to say, apart from the details, is that if you take R4 minus a line, there's a natural orthogonal complex structure on that subset. A very natural elementary orthogonal complex structure that's not constant.
So is it a conformal map? Or
Sorry?
is it a conformal map? Or
yeah, I mean everything's sort of conformal invariant. I'm saying that yeah, this is conformal. You can think of the Kähler product as conformally equivalent to the conformally flat structure. Well, I just wanted to say quickly that this example is just the simplest possible example of what happens when you have a quadric in CP3 and you see how it projects to S4. In general, things are much more complicated, and typically what happens is that in the generic case, the projection will go wrong over a smooth torus. So over a smooth torus, the two points will coalesce at points of a smooth torus, and there won't be any twistor fibers at all. Or there are two special cases in which this two torus gets pinched at one or 2 points, and over those points you have the whole twistor fiber. Or there's the case we've just done, in which somehow the torus shrinks down to a circle, and then we have this situation I've been describing. And the cones will actually, the cones I mentioned right at the start, will correspond actually to the discriminant loci in the second, in this case here, because you see a double cone in R4 that has one singular point, but it also has a singular point at infinity, so it corresponds to 2 singular points. So the last part of the talk, and I have to be a bit quicker here, is to try and relate this to these parabolas. So I want to fix this orthogonal complex structure which I've just defined. I tried to define. So this very natural orthogonal complex structure that exists on R4 minus a line, or S4 minus a circle. This is crucial. That corresponds, I've called this orthogonal complex structure JC, defined up to sign, plus or minus JC. Very natural object. And this, as I said, this really corresponds to this standard quadric in CP3. And the corresponding point, if you take a point in this quadric, the Quaternion it maps to is given by this formula, and you can think of, this is just another way of understanding why R4 minus a line is CP1 cross C plus, because we're sort of, you know, if you conjugate by quaternions, that corresponds to rotation in R3, so basically we're sort of taking V and rotating it by U to get a point here. Okay, but the other thing that comes out of this notation here, the fact that I can write this quaternion as this inverse, means that if I take any power of V, any power of this quaternion, this immediately can be expressed like this, as this sort of telescoping. And it's that fact that allows you to use this theory to deal with these quaternionic power series. Okay, now, quaternionic power series, as I said, it's obviously, they obviously define nice sort of quaternionic functions, but they don't satisfy the Fourier equations, for example. They satisfy a different notion of being analytic. They are actually sort of holomorphic on slices, the slices being those flags which I showed you earlier. Anyway, what happens is that if you do this same coordinate trick with one of these power series and you just put it in here, you see that it's the projection by the Twistor map of something genuinely holomorphic. I don't have time to explain that properly, but what it really means is the following. If you have one of these quaternionic regular maps, like a power series, the correct notion is what's called slice regular or Cullen regular function, like a polynomial or a power series, then what will happen is it will map this fixed orthogonal complex structure I defined to another orthogonal complex structure, because I'm able to define this twistor lift. Therefore, because the image of F comes from something in CP3, it has to correspond to an orthogonal complex structure. You see, if you have a map that's sort of generically it's injective, then it will always smooth and injective. It will always send a complex structure to another complex structure. But the key point here is that the image complex structure is orthogonal, still orthogonal with respect to the flat metric, or the conformally flat metric. And so these quaternionic power series have that property. And there are other maps that have that property. In particular, elements of this finite dimensional Lie group have that property, but these are not given by quaternionic power series. They're given by inverses, but you can't write that inverse actually as a power series. There may be other maps that have this property, I don't know, for which the image of this complex structure is orthogonal. I mean, you can even ask this for the standard complex structure, and I don't honestly know the answer. If you have the standard complex structure on R4, you can ask for those maps that send it to another orthogonal complex structure. That's an interesting class of maps. Now, to sort of understand this theory, I'm applying it here to this quadratic this quadratic function. Now, it's important here that I've got an IQ, because if all the coefficients were real, it would be elementary. So it's important there's an IQ here, or if it was just q squared, it would be elementary. You need coefficients not to be all real. Otherwise, the map F is sort of holomorphic in a more obvious sense. Well, obviously, there isn't time to go through all this detail, but what happens is this. If you take this very simple example, so of one of these Quaternionic regular maps, the image of the real line, and the real line was crucial because the real line came up in this picture here. I mean, the real line is this real axis. So that's the line we remove from R4 to get our orthogonal complex structure. And that line gets mapped to a parabola, gets mapped to this parabola. And lots of other things you can say. The minus a half I maps to the focus of this parabola, which is the number a quarter. Hamilton actually, in his book, explained how to solve quadratic equations in quaternions, and you need the theory of that to understand. This map is obviously generically 2 to 1, but it's actually 1 to 1 on a certain plane. Certain two-dimensional plane, real two-dimensional plane, that gets mapped to a hyperboloid in R4. Now, let me just explain this picture. This is in R4. We have a parabola in R4. That's just this image of our map with Q real. This parabola obviously lies in a plane. The hyperboloid is meant to be lying in the 3 space, which is orthogonal to this green plane, containing this line. So the paraboloid doesn't actually, it only intersects the green plane in the focus. Okay, this is a schematic large one, it's all crushed together. The parabola does not intersect the paraboloid, but somehow you get this paraboloid naturally out of the Twistor theory. The parabola determines the paraboloid in some weird way. Okay? Because this map, which obviously the parabola in a sense determines this map, once you have this map, you can look at the points where it's 1 to 1, and the image of those points is the paraboloid. You can also do the Twistor lift theory. I explained that this map has a Twistor lift. Now, the quadric is generically 2 to 1 to the 4th sphere. This quadratic map in our example is 2 to 1. In fact, the image you can calculate is a quartic, which is 4 to 1. So quartic will be 4 to 1 over S4. So this Twistor lift is generically 1 to 1. In fact, it's a birational map. So this is a sort of real picture of the image of this Twistor lift, which is given in parametrized coordinates there, and you plug it into a computer and you find the equation is this. It's a well-known ruled surface. It's a quartic, has lots of singular points. There's an isolated cusp. There's a line of cusps. There's some ordinary singularities. Edge in Edinburgh classified these things, and I think in his classification it's of type 4b or something. So it's a well-known sort of ruled singular quartic surface in CP3, and it's somehow determined by the parabola, because you see, if you take a parabola in R4 and think of R4 as in S4, so we have a parabola which I'm calling small gamma, that's contained in R4, contained in S4. You have the Twistor space CP3. You can simply look at the sort of algebraic varieties for which the inverse image of this parabola are contained in the algebraic variety, and the the sort of minimum one you get is this quartic. So the quartic is somehow naturally associated to the parabola in R4, and you can analyze the quartic you get. So as I say, because of the construction that you're starting on the left, remember the parabola is the image of the real line. Over the real line, the quadric, the real line are the points of R4 where the inverse image of the point is contained in the quadric. So when you do this Twistor lift, you see that the K has to contain every fibre over the parabola. But then you can analyze other things that go wrong, and the paraboloid corresponds to the points where typically if you have a quartic you're going to have 4 points crossing each fibre. So these it's a real quartic, so that things go in pairs. These two can come together, and when they come together as a sort of ordinary singular point, or the thing can be tangent. And the tangency is what happens over the paraboloid. So this paraboloid is sort of determined by this discriminant locus. It's a component of the discriminant locus, essentially. So I don't know, the conclusion really here is that the paraboloid, we've got this parabola in R4, it determines the paraboloid, and the paraboloid is a sort of focal set of the parabola in some sense. You can start with the parabola, try and define orthogonal complex structures. You can extend those as far as the paraboloid. But that still doesn't quite answer the question. I'm just coming back to where I started. There's this more elementary fact that the paraboloid, I mean, there's a rotational symmetry here. So I started in R3, now I'm in R4, but you can factor out by rotation in the last 2 coordinates, so the paraboloid will actually become a parabola. And the paraboloid is actually in R4, it's just the vertices of these circular cones that contain the parabola. But the new information now, this is the third part of my talk is joint work with Graziano Gentile, Caterina Stoppato, and this is now really more of a characterization of the paraboloid. There's the elementary characterization, it's the locus of vertices of double cones that contain the parabola, but the link with complex geometries, each one of these cones is actually the discriminant locus of some quadric in CP3. And there's some intimate connection, obviously the cones are intimately connected to the parabola and therefore to the quartic, and you can say this in different ways. In particular, it turns out that these quadrics, which are determined by these cones, are actually tangent to our quartic surface along some twisted cubic curve. Okay, I'll finish there. So the idea is that it's very elementary geometry that I started with, of lines going through foci, extending to cones, going through parabolas, has this Twistor interpretation. So just to finish, the parabola, which was the image of our quaternionic mapping, should now be thought of as the blue parabola. And if you look at the cones that go through that, I've now I've factored out by the S1 rotation, so I've gone back to R3. The cones that contain that parabola lie on the paraboloid, which is now this red parabola, which somehow comes about as part of the discriminant locus of this singular quartic surface in CP3. I'll stop there.
like suppose you have this orthogonal complex structure on a four-dimensional ball, which is like a flat ball, yeah. And suppose you have such structure on the ball minus the center, yeah. Then somehow, is it possible to extend, in some sense, the complex structure to this floor?
Well, what metric are you putting on the ball?
Flat.
The flat metric.
Suppose you have flat metric, and if you have an orthogonal complex structure on this complex ball minus a point.
Well, not necessarily, because it could be like, it could be like one of these things where you have to say the point at infinity.
Or maybe is there some complex completion for example, or not? Or
The problem is you could take the situation where you've got a complex projective plane that maps down, and above that single point you've got this twistor fiber.
I understand, but this is still it's kind of not a wild situation. So means that kind of.
Well, there is a completion if you go upstairs.
Yeah, but
there is an object that completes it.
Always.
Yes, I think if you have a single point, you can always do that. But if you've got more than, if the set is too big, then the problem is that the completion upstairs, when if you take the open set, you'll get some sort of analytic set upstairs, but when you take its closure, it might not be analytic anymore, it might not be complex analytic, and then you're in trouble. All these conditions on the Hausdorff measure and so on ensure that the closure upstairs is analytic and therefore sort of algebraic.
Question or comment about something that Dima mentioned when you were talking about the sixth sphere.
Yeah.
So Brun's proof says imagine I had an integrable complex structure, that would give me a section of a twistor space.
Yes.
And I can pull back the Kähler form and I get a Kähler form on the sixth sphere.
Yes.
So you could imagine a different situation where you don't demand that the complex structure be integrable, it's just an almost complex structure that's orthogonal. So it's a section of the twistor space.
Yes.
I can still pull back the symplectic form.
Yes.
And ask that it be symplectic when I pull it back, which obviously can't happen either.
Yes.
So that gives an inequality for this almost complex structure on its 9-house tensor that can never be satisfied. Has anyone looked at that, written it down?
Not to my knowledge. The other interesting observation is if you take the G2 section, then of course that's non-integrable, but its orthogonal complement. So this is a section of a CP3 bundle, so in a sense its orthogonal complement is a CP2 bundle. That is integrable. That is a complex submanifold, that's just a sort of complex quadric. So paradoxically, if you take this non-integrable almost complex structure as a section, it determines something that's sort of complex integrable.
That reminded me of another question that I had that I didn't realise was related to what you were talking about. You could do that sort of thing for any nearly Kähler-6 manifold, right? You write down this twistor space, it won't be a complex manifold, you've got this section of it, then you look at the orthogonal complement. Do you know of any?
Yes, I think that is. I think there's an old result of John Rawnsley that says that it doesn't even have to be nearly Kähler. I think if you have nearly Kähler plus some other component of the torsion, then the orthogonal complement will always be a complex sub-bundle, I think, of the twistor space. Is that possible?
I was wondering if this twistor complex, almost complex structure that's not integrable might restrict to something integrable on this orthogonal complement. Does that ever happen for examples other than the sixth sphere, or?
No, I think it would be the other complex structure if you want something integrable. It would have to be the standard complex structure.
Whichever one gives you something integrable for the nearly Kähler-6 sphere. Does it work for any other nearly Kähler-6 manifold?
Not sure, actually. I'm taking back what I said, but...
for the sixth sphere?
For the sixth sphere, the complement is integrable, but I think that's with the standard complex structure J1 on the twistor space.
Yeah.
I'm not sure what happens with the other examples.
Interesting. So no.
No more questions. Let's thank Simon again.